Okay, and so now this next video, like we were talking about there, we wanted to show some motivation for line integrals. So the first one we saw where in the previous video where we found the mass of a wire, right, that led to a line integral. Here's another scenario, right, where vector fields are involved. Here's the idea. Here's our vector field, that's all the red arrows. There's a curve C, imagine dropped into the vector field, okay? Imagine that that's the path of an object traveling in that direction. And what we want to do is we want to determine what's the work done by the force field moving that object or particle or mass or whatever along that curve. Okay. Now I wrote down here from our work earlier in chapter 12. Remember that getting work done by a force is equal to the amount of force that acts in the direction of the displacement times the magnitude of the displacement. Right, so which we derived in class, and said that because that's such a common expression in physics and engineering, we call that the dot product. It gets its own symbol, right? So F dotted with R gives you the work. All right, so here's what we'll do, like we always do when we develop a line or when we develop any integral. Actually, we start with a very, very tiny bit, and then we generalize to the whole thing. So what I'm going to do is I'm going to take a tiny portion of that curve. I'll put that over here. Okay, and we imagine, gang, that the displacement of an object from this end to this end. Now remember, it's a very, very tiny differential displacement. So let's call that dr, okay? And the force vector, we'll put a force vector on there so we can see that. Here's the force vector. And the angle that it makes with the displacement vector. So in this scenario, in this situation right here, what's the work done by the force moving the object along the green path? It's approximately equal to, getting this expression right here. Okay? Right? It's not a big leap from the work that we did in chapter 12, right? This expression right here. So now we imagine that the whole curve is made up of these tiny differential pieces. And so the work over each one, the differential amount of work over each one is going to be equal to this expression. And what do? We sum them all up to get the total work done by the vector field on the object along this path. Okay? So the total work then right, is where we sum up all those differential elements over the entire curve C. Okay, and this is another example of a line integral. Okay, so we'll see other ones to be sure, but this right here, again, this in the context of this problem represents the work done by the vector field moving a path, particle, or moving an object, particle, whatever, along that curve situated in the vector field. Okay, here's something else you might find interesting as well. Okay, that look about right to you, guys? Notice the differentials dt right here. Okay, and so it's equivalent. Okay, do you remember what this is? Yeah, that was the tangent vector, right? That was the tangent vector. Okay, I'm going to write that like this, and I'm going to do one more step. Okay, so what I did was I multiplied by a clever expression of 1. Okay, so I'm going to go up here, okay? Now, what is this expression? This is the unit tangent vector. Okay? This right here, again, do you remember what this was? From our work in chapter 12 and also from the previous video? Good. That's ds. Okay? So our work integral that we developed here is also equal to this. Okay? Now, this may appeal to a lot of you that are in physics and engineering. And what this one says, if you remember the notation that we used back in, was chapter 12, section 12.9, I think it was, when we're talking about acceleration. This is referred to as the tangential component of the force. So what this tells us then is that the work done by a force field on an object moving along a curve is due entirely to the tangential component of the force. Okay, entirely to the tangential component of the force. Okay? All right, so in PenCast, we'll see a lot more examples of this stuff, but this is a good introduction, I think, for us, gang, for the stuff that we're going to be doing in the rest of chapter 15, okay? Line integrals.